thank the organizers for inviting me. I mean, it's a really great pleasure for me to be here. Now, as the title implies, what I'm interested in is to understand, on the one hand, the approximation properties of deep neural networks and relate this, on the other hand, to the complexity of those neural networks in terms of sparse connectivity. And this is joint work with Helmut Bölzker from the ETH in Zurich, Philipp Groß from the University in Vienna, and one of my postdocs, Philipp Petersen from TU Berlin. So over the last years, I mean, also in areas of mathematics, we have seen that deep neural networks and deep learning had tremendous success. And I would like to start with a couple of examples from those areas. For instance, in imaging sciences, there are denoising algorithms, for instance, one by Burger, Schuler, and Hamelink in 2012, which uses deep learning techniques and which outperform basically everything what has been done so far, in particular also, for instance, BM3D. Then in inverse problems, one example is limited angle tomography, where you in a way want to compute line integrals and you are missing a certain angle because the element there is fixed. And it was always before infeasible in some sense to recover the data in this missing angle. And now using those techniques now, people can do that. Also in the area of PDE solvers, there is, I think, very interesting work by Klaus and his collaborators with applications in material sciences where they solve in a very fast way the electronic Schrödinger equation. So these methods, in a way, as I said, outperform classical methods, which we have worked on for a long time. And so what my interest in this is I would like to develop some mathematical foundations for those tools to then also be able to compare them on a theoretical level with existing methods, and in particular also maybe combine those to get the best out of, let's say, both worlds. So in this talk, I would like to take an approximation viewpoint. I'm interested in the following, let's say, question. If you have, so typically in applications, you have a, let's say, highly complex function in the background, and what you aim for is with your neural network to approximate those functions giving certain sample points. And so you see some examples here. If you have a classification problem, for instance, in imaging sciences, we typically assume that the images lie on the lower dimensional manifold in high dimensions. And so you can imagine that, for instance, some images, let's say images of dogs, you have on one part of the manifold, images of cats on the other part. And if you would like to solve a classification problem, what you want to learn is a function defined on the manifold, which in one area gives you, let's say, one value, in the other area, a different value. If you have much more complex data, what you then aim to learn is a function defined on the high dimensional space Rn, maybe even with output in Rm, if you have, let's say, as an output a speech sequence. And so in this talk, I will first focus on this situation, so functions defined on the full space Rn, and then in the last part, I will just briefly show you how these results can be actually easily transferred to the setting of functions on lower dimensional manifolds. Yeah, we all know, I mean, neural networks or deep neural networks are now that powerful because we have the computational power to train those. But still, I mean, if you have hundreds of layers, it's a huge computational challenge, and one way out are sparsely connected networks. And so what I found, for instance, interesting as an interesting application in speech recognition, before speech recognition could be performed only online, so everything was computed in the cloud, but now using sparsely connected networks, we can do that actually offline. And so in my talk, what I'm interested in is I would like to relate the approximation accuracy of deep neural networks with the complexity of those approximating neural networks, and I would like to measure the complexity in terms of sparse connectivity. And so these are the key questions I would like to ask in my talk. If I aim for a certain accuracy or a certain error, how many edges do we need to reach that? And what we will see is we will get a conceptual lower bound on the number of edges we definitely need for that, which is then a bound in some sense which every learning algorithm has to obey. Then you can ask, I mean, this bound, is it a sharp bound? Can you reach this bound? Are there networks which are in a way optimally sparsely connected in this sense? And we will see that we can actually construct such neural networks explicitly. So the bound is sharp, and yeah, I will show you how we can do that. And then in the third part, certainly now you can ask, I mean, this is nice, there's a lot of theory, but what happens in practice if I have ReLUs and if I train everything by backpropagation? Do I reach this bound relating approximation accuracy to sparsely or sparse connectivity? And we will see that indeed, I mean, if we take certain network topologies, we are able to almost reach this optimal rate. So this is what this talk will be about. Good, so let's start slowly and let's fix some notation. So this is how I view a neural network. So D will be always the dimension of the input layer. So here it would be 4. I'm interested in the number of layers. The number of neurons. Rho will be always the rectifier. These I will denote the affine linear maps by WL. So a neural network in my setting here is a function of this type, where I apply each time an affine linear map, which I denote by WL, and then a rectifier component-wise. So it could be a ReLU, it could be something else. And also, what I'm particularly interested in is the number of layers, and then the number of edges with non-zero weight. These are typically, will denote by M. And D, as I said, the dimension of the input layer, and rho the rectifier. So this is, when I write phi in neural network LMD rho, this is what I mean. And so what we are interested in is to have a small m, so to have a small number of edges with non-zero weight. That's what I call, and everybody calls, sparsely connected. Now, if we look at approximation properties, I mean, there's a famous theorem which we already saw yesterday, during yesterday's talk, which is the universal approximation theorem. So it basically says, and I recall what we heard also yesterday, if you have a continuous function on a compact set, we can approximate it arbitrarily well with a network with one hidden layer. So this is the precise statement. So f is my function, I have an arbitrary accuracy, and this is the function which is given by a network with one hidden layer. But then you can ask the question, I mean, now from the perspective I would like to go to. You see, on the one hand side, you have the approximation accuracy, but, I mean, this result doesn't tell you much about the complexity of those neural networks, because it doesn't tell us, for instance, how many neurons do you need, and also what is maybe the optimal sparse connectivity in this setting. Now, so this is certainly not the only result in approximation theory. There are many results, and also we heard a beautiful talk yesterday about another result also looking at approximations. Still, I mean, if you look through this literature, the question I'm asking, relating approximation accuracy with sparse connectivity, there isn't much being done yet. And so this is what I will talk about in this talk, and we will start with analyzing whether there's a lower bound on the sparse connectivity. And let me start in a, let's say, higher level viewpoint. So what will our result says? Well, first of all, when we fix an input dimension and we fix a rectifier. Then I fix the function class I'm interested in. So I fix the input dimension, I fix the rectifier, which I apply at each level. Each layer, then I fix a function class, and then I fix a learning procedure, and this learning procedure, as usual, takes an accuracy, it takes an element of my function class, it outputs a neural network which approximates that function class with that accuracy. And the result will then say there is a fundamental lower bound on the number of edges these networks have to have. And this lower bound is in terms of what's called the optimal exponent of this function class. Now, what is this optimal exponent? That comes from information theory, from rate distortion theory. It's just viewed as a measure of the complexity of that function class. I don't want to go too much into the details there. What it basically does, it takes this function class, it encodes it as a bit sequence in such a way that a certain accuracy is kept. So if I transform it back, I get a certain error, and then I let the error go to 0. And this is the rate in some sense, to which this then, the length goes to infinity. So this is the optimal exponent, which you will see also in the precise statement on the next slide. So let's take a look at the precise statement. So this is my learning procedure. I take an accuracy, I take an element of my function class. So here I consider functions this case of L2RD, and it outputs a neural network where I don't care about the number of layers, I don't care about the number of edges, I just care about the input dimension and the rectifier. And it is done in such a way that the error which I make when I'm approximating this class is bounded by that epsilon. And then we can show the following. If we take a gamma, which is less than this optimal exponent, there does not exist a constant c, so that the number of edges, which we have here, or the number of non-zero weights in these networks, is bounded by a constant time epsilon to minus gamma. So what does it mean visually? Let's say this is here my epsilon, this is my number of edges. So I have this bound, which is maybe this red curve. So this says the number of edges in these approximating neural networks is in some sense above this curve. So as epsilon goes to zero, for instance, the number of edges has to grow faster than epsilon to minus gamma. Okay, so now you can ask the question, if I let the gamma grow, certainly this curve will go steeper and steeper. Maybe at some point I reach the limit. So maybe then I find neural networks which actually have that sparse connectivity. And so I can now ask the question, what happens if gamma is equal to gamma star of c? And you will see that that's the limit. There you can construct explicitly neural networks which have an accuracy of epsilon, let's say, but which have also that sparse connectivity, so that we indeed now find a C, so that we have this bound. Okay, so that's now the next task, to create and to construct these optimally sparse neural networks. So what are the key ideas? The key ideas is, in, let's say, function approximation, we have a rich set of methods to approximate such functions with representation systems, like Garber wavelets, Garber systems, and so on. And so this is typically done by looking at linear combinations of those elements, maybe of n of those. So the idea is now to mimic these approximations, these n-term approximations, or these linear combinations by neural networks. So then the outcome will be deep neural networks have as much approximation power as classical representation systems. Think of wavelets or systems like that. And certainly then, since we are interested in sparse connectivity, we need to control also the number of edges of these neural networks. Okay, so that's the key idea. Now, the essence of the result we will see in a moment is as follows. Let's assume I have a function class and a representation system where I know this gives me the best approximations of my function class. And there are various examples for wavelets and so on. Then I want to mimic the approximation by a neural network. And if this neural network does what it should, that it approximates this class with that accuracy, then we can show that the number of edges is indeed now bounded by epsilon to minus gamma star of c. And we saw before, this is the optimum. It cannot go below that. Okay, so that's now the goal. So let's just very briefly recall what I said here, this n-term approximation. Okay, so I have my class of functions. I have a representation system, wavelets, maybe Fourier, whatever you can think of. And I want to measure how good this representation system approximates my class. What I typically do is I take an element of my class, and let's say I have a budget of m, and I'm allowed to take m elements of my representation system, and I will do it in such a way that I build a linear combination which then best approximates my f. So I approximate, that's the key point, by linear combinations of, let's say, m terms. And then, people are interested in what happens if now I increase my budget, then certainly, the error will go to 0, and the question is at which rate. Okay, so what this does is basically it relates approximation accuracy to the complexity of the approximating system, and here I measure complexity in terms of classical sparsity because I'm interested in taking very few terms. But the key point here, which you should take from this slide, is that classically I approximate functions by such linear combinations. Okay. Good, so now let's go into the world of deep neural networks. Let's assume I have my favorite representation system, and let's assume I can do the following. For each element of my system, I now build a neural network which realizes that system, which realizes that function, sorry. Yeah, for each I create a neural network where I can control the number of edges, which realizes that function. Yeah, so let's assume I have a function from R2 to R, and let's assume these my networks which do that have this form. So these are functions from R2 to R. Okay, so what I'm now interested in is a linear combination of m terms. So what do I do? How do I realize this by a neural network? Well, I take my little networks, I plug them together, you can see here, and then I combine them. And the weights on these edges are exactly these CIs. So I have my little networks, I combine everything, and then I combine that in one output. Now, how many edges does this network have? These little networks have all a constant number of edges. I combine m of those, so this network has O of m edges. So that's what I need to control. Good. Okay, so let's assume I can do that. I can realize every element with a neural network. That's the first part here of this slide. And now let's assume I have a function class for which this system is best in some sense, so that the error which I make, if I approximate this now with a linear combination, behaves like this. And let me just say this is the optimal rate you can achieve. Then, if we have that, what follows is every function can be approximated up to an error of epsilon by a neural network with this number of edges. This is what we need. And now if we go back to the previous slide, this was the statement just copied. So if we have this, then we know there exists now a C, so that this is bounded by C times epsilon to minus gamma star. Okay, so what we need to do is we need to get this to work, and these are the tasks. I need to find a class of functions. I need to find a representation system, which gives me an optimal approximation of my class of functions, and so that I realize every element of my system by a neural network with a controlled number of edges. So that's the program. There are many examples you can now work through. Let me show you one. Okay, so one example for representation systems are what we call shearlets. These are systems which we use for sparse regularization of inverse problems. You see elements of the system here. Now, how do those work? You see there are several components. You have, first of all, you have a translation, so you move things, let's say your shearlet element on the plane. You have a component which changes the scale. It's a multi-scale system, and it changes this in an anisotropic way, because in the end, you would like to typically approximate some curvilinear structures, and you also have a means to change the orientation. This is this shearing matrix. And so there exists a whole theory for those systems. What I think quite interesting here is that this part is an affine map. So if we want to realize these elements by a deep neural network, what we just do is you need to realize these functions. This part we can do just with one layer. And so this is actually true for most of the systems from this area of applied harmonic analysis. We extend it slightly now to get a bit more flexibility. So what you see what happens, we extend this matrix by introducing now a parameter alpha. And the advantage of this is that now we have a much larger range of systems. Maybe you've heard of wavelets. This is what is used for JPEG 2000. So for alpha equal to 1/2, we have shearlets. For alpha equal to 1, we get wavelets, which are isotropic functions. And for alpha equal to 0, we get richlets. So this is in a way the other extreme. Okay, these are my systems. Now I'm wondering what class of functions is best for them. There's the notion of cartoon-like functions introduced by Dave Donahoe in 2001. We then extended it, and basically, I don't want to give the precise details, but let me just say these are functions. So the function looks like this, for instance. Supported on the unit square, smooth apart from a discontinuity curve, which has some regularity depending on this alpha. So one viewpoint of these is that these are functions which kind of mimic essential properties of images, like governing by edge structures. And with these alpha shearlets, we can show that indeed these give optimal approximations of these functions. Okay, so we have a class of functions. We have a representation system, these alpha shearlets, which give optimally sparse approximations of these functions. That has so far nothing to do with neural networks. So now we need to go into that world. And what we need to do now is each element of my shearlet system I need to realize by a neural network so that I can control the number of edges. So let's maybe go back. So I need to realize everyone with a neural network. Okay. So how do I do that? Actually, the key idea, or let's say early ideas, were already when I was in New York. Jan LeCun told me in his PhD thesis he already had early ideas how to build functions using these neural networks, in particular functions of this type. And then it was refined in recent work by Schaam, Cloninger, and Kaufman. So what did they do? They took ReLUs, they built a bump function using those. Then they went to 2D by combining those in a certain way. Now, if you have this 2D bump function and you shift it, you can create what we call vanishing moments, which are important for this theory, and you can realize by a 3-layer network. For us, we need one technical detail because these does not yield differentiable functions. So what we do in our theory is actually we smooth out the ReLU so that it becomes differentiable, and then we basically work through the whole program. Okay, so now we can combine everything. We get our optimality result, or one version of it. If we have these cartoon-like functions, and for each n we find a neural network with O of n edges, which approximates this function with this accuracy, and this, in fact, is this gamma star. So I have here the accuracy of n to the -1 over gamma star. So this is now a neural network which is provably optimally sparsely connected with a certain accuracy. Okay, so we can transfer everything to manifolds. So I don't want to go too much into the details there, to functions on the manifold. There's a canonical way to do that. For a manifold, we have an atlas. We can create a partition of unity and then represent functions like that. So this can be done, and there's a straightforward way to extend that. I would like to finish in the last minutes to show you some also numerics. So what is our question now? What happens in reality? And what we want to do is we want to fix a network topology. So we want to take these networks and train them. What we take are ReLUs as a rectifier. We learn through backpropagation, and then we are interested in the relation between the approximation error and the number of edges. Okay, and we want to take, let's say, toy examples, very easy functions, and then see what happens. Okay, so these functions will be functions very easy from R2 to R. This is my first function. So that's a function from R2 to R, and I want to train my network to learn that function. So it's a classification, you can view it that way, but it's basically a toy example. Good, so I take point samples and I train that network topology which you saw before. What we then see is that the number of edges related to the approximation error indeed behaves exponentially, and this is also the optimal rate, because from our theory, we know that for those richlets, these shearlets with alpha equal to 0 are the best, and they would give me also this rate. Okay, so that's in a way the, let's say, optimal and optimality. So we can recover the optimality result also in practice. And now we can also ask the question, and which we found actually quite exciting, what happens in these subnetworks? So you also learn functions there. These are again functions from R2 to R. And then you can look at those where these weights are large. How do these subnetworks now look like? And this is how they look like. And we were actually quite fascinated by that because these are very much like richlets. And from the theory, we know that these are the elements of a representation system which are provably optimal for approximating such a function with a linear singularity. Okay, so let's finish with a second example. We make it a little more complicated. We take a curvilinear singularity. Of this, we know shearlets are the best. the rate of decay, if we train our network, is now m to the minus 1. And again, this is the optimal rate for shearlets, so alpha shearlets with alpha equal to 1/2. And again, let's look at these, let's say, little networks, what we observe there. And these are the functions which are trained. And again, I mean, these functions are kind of close to the shearlets we constructed in a way explicitly to reach optimal approximation properties. So in some sense, in these little networks, the learning algorithm automatically learns approximately those functions which we know from applied harmonic analysis best approximate the general function. And so we even have elements at different scales, so if you plug them together by hand, we can create even something like a multi-scale approximation. Good, so let me conclude. In general, we were interested in relating approximation properties of networks with the complexity of those networks, and the complexity we measured in terms of sparse connectivity. And we asked the following questions: how many edges do you need for a certain accuracy? What I showed you is one result, which shows that in some sense there's a fundamental lower bound for the number of edges you need for that accuracy. Then we asked the question, is this bound sharp? So can we create networks which in a way reach this optimal, let's say, ratio between the accuracy and the sparse connectivity? And indeed we could do that. The key idea was to transfer results from function approximation by representation systems now in the world of neural networks. And the last question was, what happens in practice if we now train a network by backpropagation? We took a specific architecture of the network, and we showed that in fact in easy examples we could reach this optimal bound. And what we found also interesting is that in these little networks, the trained function in a way looks very much like these multi-scale systems we know very well from applied harmonic analysis. And with this, I'd like to conclude, and thank you very much for your attention.
Thank you very much. We have time for a few questions.
Quick question. So there's some recent work on sparse dense training, where basically, you may have seen this. This came essentially out of the D5 work in Stanford, where they basically train networks, then use a number of essentially heuristic hacks to eliminate some coefficients, and then retrain the remaining weights, and then let the sparse weights become dense again. And that seems to yield a slight improvement. Any comments or thoughts on that in this relation?
Well, I mean, what I can say is that these results which we have here, I mean, if you, so let's maybe put this on again. So these cannot be beaten by learning algorithms. So if you're in this setting, it would be, I think, very interesting to maybe look at this procedure and maybe combine it with these ideas to maybe in a more sophisticated way eliminate those, or maybe even start in the beginning with a network topology which might already be better adapted to sparse connectivity. But I mean, these are just some thoughts. I mean,
no, because you're effectively then optimizing around a specific sparse structure with a small modification there. Okay. Anyway, thanks.
Thank you very much for the talk. And so I was wondering, the lower bound you get depends on an information theoretic measure of the complexity of the function we want to learn. In case this is a classification task, do you have an explicit way of knowing what is this information theoretic complexity? So if I give you a specific data set, what should I expect it to be related to?
So I guess, I mean, what could be done, I mean, let's say defining a class which maybe solves classification problems adapted to that, and then compute the optimal exponent for those. Yeah, so this is always over a class, but maybe you can design a nice, let's say, class of functions which are relevant, let's say, for maybe a class of classification problems, and then go through this route, learning or computing the complexity, and this would give you then the error bound.
In any way, this bound is on the complexity of the class we are using, not of the
Yeah.
specific function we want.
That's right. It's always over the class.
Okay.
That's right. I mean, there could be some, let's say, which are different, but it's yeah.
Okay. Thank you very much.
The way I understand neural networks is that the representation can effectively have multiple scales. So in a way, this would mean probably in your theory that the representation system has to have certain properties. So you would have to fix that before. Is that, I mean, I mean, the question is, what about some multi-scale properties in your
Yeah, so this is
theory?
not explicitly used here. So the way we do it is, let me see, yeah. So basically here we treat the different scales in the same way. Yeah. So we have our function, let's say this function. We realize this psi by this little network. And then, I mean, we have all these different parameters, but then we put them next to each other without caring whether some have a different scale than the other. Certainly, I mean, what you said, I think would be very interesting to use that in some way and maybe combine them in a different way, taking care of the multiscale property.
So, I mean, the way I understood Tommy was that the fact that you use the deep structures actually allow you to be a bit more efficient. So in that sense, your bound is a very conservative one.
That's right, but sorry. So what we also consider, so he considered these compositorial functions, whereas we consider here just arbitrary function classes in R2RD, which don't have any hierarchical structure per se. So therefore, what we do is we basically just mimic what is done from function approximation in that sense. Yeah, so I think there's a slight difference, but still I think it's a very interesting idea, maybe to combine it in a different way, to also then maybe optimize what. So here, I mean, we don't actually take the number of layers into account. This is not important for our analysis, but that would be interesting, an interesting perspective.
So in a way, if you think about it, then of course you can always translate a neural network into a kernel method, and then you have the function class, which can be very complicated. But basically, you're taking this approach. So you're going to some Hilbert space, and then you're proving your things there.
Yeah.
So that's I mean, I think the debate is how the hierarchical structure actually helps. So that I think. But can you think about ways of including this? Have you thought about it?
Not yet. I mean, we just finished this work actually maybe 2 or 3 weeks ago, but I think that's an interesting direction. So as I said, I mean, here we were interested just in sparse connectivity, not caring about the number of layers, but including that, yeah, so maybe exploring this multi-scale structure, maybe also looking at very specific function classes, because you can also go, let's say, from approximation theory, there are certain approximation spaces which are canonically defined. In approximation theory, you can maybe try to also introduce those for neural networks, exploring more the structure of the depths. But I think for me, this would be work for the future.
Okay,
Yeah.
so thank you very much. Unfortunately, we have to cut down the discussion and postpone it to the lunch break.